hello from me. As Gil said, my name is Ida, and I am an Allegro fellow here at the Alma node in the Netherlands. And today I will be telling you about this tool that we've developed recently that we released in July called Alminer. So the title of today's talk is basically a demo of Alminer, which is the Alma archive mining and visualization toolkit. So yeah, as I mentioned, I was one of the people leading the development of this tool, but this was in collaboration with Alvaro Hakar, who is an assistant professor at the Institute for Astrophysics at the University of Vienna in Austria, and he's also the PI of the ERC starting grant called Emerge. And so this project has been in collaboration with Alvaro as part of this starting grant project. Alvaro is also here in the panel, so he's waving. And so if during the discussions, he will also chime in on his thoughts. Okay, so what is Alminer? Alminer is essentially a Python-based code that effectively queries, analyzes, and visualizes the content of the Alma Science Archive. And so basically, the idea is to go from, I wonder what Alma has observed for X, Y, and Z, to something that shows you the answer to this question more visually. So if you kind of understand, for example, in this plot is one of our main plots that we create in Alminer, where you can see kind of the frequency distribution of the observations that you're interested in, and then you can kind of narrow down your question from there. So the idea has always been to basically make this connection as smooth as possible and as easy as possible for users. This is why we wrote a Python-based code with a series of basically functions that are easily used. And this is what I will be presenting to you, all the different functions of Alminer today. And one bonus part of Alminer is that we can also directly download Alma data products using Alminer, but through AstroQuery for the download. And so everything can be kind of self-sustained. A whole project can be done with Alminer all the way to the data download part. So where can you find Alminer? So our main documentation is through Read the Docs. So if you go to alminer.readthedocs.io, you will land on this page, which will basically tell you how to install it, the dependencies, how to get started, etc. And there's a series of tutorials, which are actually the bulk of what I will go through today. The code is also open source. It's on GitHub. And if you go to the GitHub page, you will land here, which is kind of similar to what the Read the Docs was. So you can get installation information and how to get started. Okay. Now, the installation is very simple. You can actually just do pip install Alminer. Depending on your installation system, you may need to do pip 3 for Python 3. And our dependencies are basically so we use Python 3.6. This is a little bit dependent on AstroPy, as that's the version that they prefer. And then the main packages that we rely on are NumPy for calculations, Matplotlib for the visualization, Pandas, which is a data frame sort of system where you could kind of analyze a lot of data. Pivo is what helps us connect to the Alma archive directly, and AstroPy for various functions that are really useful with AstroPy, like the coordinate systems and so on. And then, as I mentioned, for the data download, we rely on AstroQuery. So let's get started. This presentation is a live Jupyter notebook. So I have it in slide mode, so I can show you each build. But you can also follow along with me. I think the panelists have, Carmen has put this in the chat for you. So if you go to bit.ly, alminer_itrain, you can get to the notebook. And there's also a static version, but the static version is a little bit behind. It's not as refreshed as the active one. So once you go to this link, you will land on the actual, so I can also take you from the Alminer GitHub. If you go into notebooks, we have a tutorial folder, but we also have this iTrain. And if you click on this Launch Jupyter Notebook, Binder will open the Jupyter Notebook for you. This will take some time, to just like a few minutes to get started, but then you will see the slides that I will be showing in a few minutes. Okay, so the outline of the tutorial is basically to go through all the functions that we have available. So basically to go from the initial idea of like, what are you looking for in the archive, to then filtering the results that you're looking for, and then visualizing those findings. So whatever you filtered down, you can create plots to visualize those, and then from there you can create reports of these plots, or you could create tables of the data that you're interested in, and then you could download the data. So this is the progression that I will follow. Now, first, we need to import all the relevant packages, which is not that many. So technically, you just need to import Alminer. But if you want to do a little bit of filtering using pandas, you have to import pandas. And if you want to play a little bit with catalogs, for example, you need a package that would read ASCII files. So in this case, I have used AstroPi's ASCII package. Okay, if you have the Jupyter Notebook running and you've gotten to this stage, and you press Shift Enter and it went through fine, then you are fine to continue along with me. Okay, so the first thing we will tackle is all the different query tools that we have available. So there are three main different ways of querying the Alma archive. The first is, you know your source name, and you want to basically see how many Alma observations have been done for this source. The second is the position, so you know some position in the sky, right ascension declination, and you want to know what was observed in that direction. And the third is Alma Keywords. So by Alma Keywords, what I mean is when you go to the Alma archive, so this is just the main Alma archive web interface. So the keywords are basically all the different columns that you see here. So all these different options that you have also here when you click. So sorry, lost now. So the keywords will basically help you with ideas. Let's say you have an idea, I want to know what was observed in the field of high mass star formation or protoplanetary disks. The Alma Keywords is where you would go. Okay, so let's begin with a little bit of an overview of what all of these functions have in common, which is that once you query using any of these functions, what is returned is actually a pandas data frame. So you could use this data frame however you wish to filter it down, which I will show some examples of. But by default, we will query public data. There is a possibility, a parameter that you could set to false. So if you set public to false, you will get all the proprietary data. And if you set public to none, you will get both. So you will get both public and proprietary data. By default, we also write in a summary of the target names in your query. But you could imagine for a big query, like if you're querying an entire field, that this would be really a lot of source names. So there's also a possibility to turn this feature off, which I will show briefly. Okay, so the first query function is querying by the target name. So in the top right, I will always mention the name of the function. So this is target. And the requirement for this function to work is that the target must be resolved in one of these three databases. So either Simbad, NED, or Vizier. So these should be more like well-known objects, let's say. And then what the code does is it retrieves the coordinates from one of these databases, whichever it found it in, and then it will do a cone search essentially. And for us, the default search radius is 1 arc minute around the position of the coordinate that was found. Just to link it back to the actual archive, when you go to the archive, this is exactly what is done here. So they also go through Net, Simbad, or Vizier, with the exception that the default radius is 10 arc minutes. So for us, it's 1 arc minute, but you have the option of changing this. Okay, so let's do some examples. If you want to query 2 sources by name, for example, Orion KL and AB or totally different topics, you would put it in, so you would basically give a name to your query. So this will be the data frame that you can play with after. And the function you can call according in this way, alminer.target, and then you put the names of the targets you're interested in as a list. And what the summary that is printed is basically an overview of what was found. So in the case of Orion KL, we found 35 public projects. The number of observations are 91. And then we divide the subbands into 2 lists. One is the unique subband and one is the total subband. This is very useful if, for example, you're querying one project, in which case you may have many observations within that project, but there would only be, let's say, a handful of unique bands, so a handful of unique spectral windows. And then we also specify how many unique targets were observed. So 40 targets were observed for this search. And then these are the names of the sources. Also note that it's this naming that is specified here is based on what the PI decided to set as their target name. And then this is the example for AB or A. So you can see the different naming conventions here better of what have been called. So you have to always be careful with the number of targets, because this is still 1 target, but because they're named differently, they show up as 3 different sources. Okay, so now let's increase the search radius. So we can use this search radius parameter and set it to 5. Default was 1, and you can see that we end up with more projects. So if I go back, you could see that before we had here 317, but now we have 7, 8, and 38, so many more. But you have to also notice that when you increase it really depends on your case. If you increase your radius around a point source object, you end up including other sources. So I think I actually have the case of ABRK open. So here you can see this is a target you may be interested in, but if you look at a big cone around it, you start including other sources you may not be interested in. Okay, let's go forward. So the next example is, what if you want to query a list of objects? You can basically create your own catalog. So in this example, I have created a catalog where I have the first column, the names, the second, the right ascension, then the declination. And I can basically use the same alminer.target function to query for the names. You have to be careful that the target function will query based on the name. So it will look for these names in Simbad, Net, and Vizier and get the coordinates from there. It will not take the coordinates from your list. There's another function you can use for that, which I will talk about briefly coming up. So in this example, I can basically read my sample catalog, which is this what I showed you here. I tell it where the header starts and where the data starts. And then I can basically feed the column of called name, basically all these sources, to the alminer.target. And then it will print out for you what the query returned for each of the different objects in this list. Okay. Now, if we want to include proprietary data, as I mentioned before, we just set public to none. So in this case, we are looking at both public and proprietary data. And so you will end up with more projects, but you have to be careful that then later in the data download, you may have an issue with proprietary data. So that's why we have the default as public. Okay, the second query function is querying by position. So basically, you know your right ascension declination of a position in the sky. And you know what search radius you're interested in. So in this case, we could use the cone search function of Alminer, which then also has an add-on, which is the catalog function. So let's start with an example. Let's query an object very simply by its coordinates. So let's just say the right ascension declination, these have to be in degrees. You can always use AstroPi to convert between different conventions. And here I have selected a search radius of 10 arc minutes. This is sen A, and you can see how many projects were found, how many observations, and individual spectral windows. Now, if you have a catalog of objects and you want to query them by their coordinates, you would do similar as what we did before, basically read the ASCII file, which is your catalog. And in this example, for example, I have Spitzer sample.dat, and it's a really, really large catalog of WISOs in Orion. I think I can show you here how it looks like. So the Spitzer sample looks like this. So it can have however many columns you have in your catalog. The only thing that's important is that you need to have two columns, one for the right ascension and one for the declination. And then you will basically tell it which columns it should basically pick. So for me, the column called sequence, SEQ, I want to give to the parameter name. And then I also set the columns for the REN deck, and you run the query through alminer.catalog. And then this will basically, so for, to make it go faster, I just was interested in, let's say, 3 rows of the catalog, but it will basically write out the summary for each of the targets in your query. Okay. Now, the very interesting way of querying the Alma archive, the what we call key search, so searching by keywords, is basically querying for any of the columns that you see on the Alma archive that are string type. So this is very powerful because then you can kind of create queries based on ideas, like you can look at a certain field, you could look at what's in the proposal abstract, what's in the scientific category, etc. There are some rules that we have decided on. So the nomenclature is in this way. So you can basically give it a dictionary of keywords. So here you can see I have done proposal abstract and scientific keyword. But in the proposal abstract, I can say, okay, I'm interested in the field of high mass star formation. So I'm going to look for which proposals in their abstracts have had high mass, star formation, outflow, and disk. And when you put spaces in between, so if this is all in one quotation, it will interpret it. It will interpret the spaces as and. So you're looking for having all these keywords in the abstract for sure. If you want to do OR logic, you can separate them out. So basically put a quote around each of the words you're interested in. And in that way, it will do OR logic. And then really powerful is actually combining different keywords. So here I'm looking for star formation projects, but in the category of galaxy evolution. So then you can kind of, if you are only interested in extragalactic work, you can kind of make sure that you're getting what you want. The columns in the Alma Science Archive, you can definitely go by those to figure out basically what you can, what parameters you can give to this function. But we've also created a table on our read the docs. So if I open this table, so this is down here, query keywords. we've created a table of all the possible keywords you can use, their type, and the description of what you could be searching for. So you could, for example, even search for authors, really anything that you see here. Okay, let's look at some examples. So in this example, I want to still search by the name of the object, but the name of this object may not be resolved in Simbad, Net, or Wizir. In this case, you would use key search and use the target name parameter. So in this case, if you imagine like in my field in star formation, when we find all these molecular clouds that fragment, each of these cores will not necessarily be resolved in these famous catalogs. And so this is really useful because there are many famous sources that may not be in these types of catalogs, but that you can query for using the key search function. This is equivalent to, if you go to the Alma archive, to this second query to the Alma source name. Okay, now we can search by proposal ID. So if you know you're interested in one particular project, this is powerful, for example, for large programs that have a lot of data that you may be interested in, and you want to just narrow yourself to one project to make the spectral setup simple to deal with, etc. Then you can use the proposal ID parameter to search for particular projects. The next example, you can search the proposal abstract, kind of what I talked about in the intro of this function, and you can choose this print targets option to be false. So for example, if you're looking for entire fields, you have here 259 objects that you may not want to print out to the terminal to see, to kind of make it neater, but you can always toggle it back on. Okay, as I said also in the intro to this part, you can combine keywords. So in this example, I've combined high mass star formation or massive star formation. So for example, if there's an ambiguity in your field, so sometimes people use high mass star formation, sometimes massive star formation. Here I can look in the proposal abstract for high mass star formation or massive star formation, so it will catch either or. Within the scientific category of galaxy evolution. And because there are so many targets, 1,376, I don't want to print the names to the terminal. For polarization data, you can basically set the pol states keyword to XYYX, and then it will catch those. So here I've combined it with the scientific keyword of disks around low mass stars. So going back to actually these scientific science categories and scientific keywords, if you go onto our read the docs, we also have two tables for all the possibilities of what keywords and categories you can use. So if you click on categories, you can see these are the categories that have been ingested in the archive's metadata. And similarly for the keyword, it gets more descriptive, but then you can kind of look here and see what's relevant for you that you could search for. Okay. Now that we've created our queries, either by name, position, or keywords, we can use the resulting data frame to narrow down our search even more. Because so far you could only search for, let's say, string type keywords. But what if you wanted to look at, for example, only high resolution data or only ACA data, etc. This is what you can do with basically what I have been doing is with pandas. I think there are other packages that you could use also, but I recommend pandas because Alminer has been created based on pandas. So I'm going to go through some of the options that you have, but this is definitely just a very superficial list of sort of what I wanted to highlight. There's a lot you can do with pandas. Okay. So let's create a query first that we can then use for the rest of the tutorial. And I can show you all the different filtering afterwards. So the query that I will create is a very broad one so that we get a lot of projects that we can kind of look at what has been observed for. So in this case, I looked at the science keyword galaxy chemistry. So apparently there are 47 projects and 63 targets in particular. So let's keep going. So using this, so if I go back one, you can see that you can set this to whatever you want. So I've set it to observations equals and then run the query. But whatever you set here will be your data frame. So this is what you will be working with. So what we can do, the first thing we can do is actually to have a look at what is there, right? All these summaries that have been printed. To do so, of course, you can just write observations in the terminal and you will get the full table. But if you have really, really large queries, it will always truncate the table. It will not show you all the rows and not all the columns. So for that reason, we've created a function called alminer.explore. And with explore, you can basically toggle on and off, basically whether if you want all the columns to be shown, all the rows to be shown, and you can kind of play with it that way. The default is that we only show the 18 most useful columns. And if you're interested, you can turn it off. So here, for example, the query that I ran that was called observations, I can write alminer.explore observations. And here you can see that it's just showing 18. If I can maybe scroll. There are 18 columns. And if I scroll down, you can see there are 1,361 rows. Now, if we then want to show all the columns, what we can do is alminer.explore observations, the data frame name, and turn all calls to true. I will keep all rows to false because showing 1,361, whatever it was, rows will sometimes take a long time. You can definitely turn it on and have a look. It's mostly useful for smaller tables, I would say. But here you can see, I'll scroll down. So you can see that there's 1,361 rows and now 81 columns. So if we go all the way back up again, you can see that we have all the 18 columns that we had, but now added is all the different columns that you also find when you go on the web version of the Science Archive. So these are many, many, many different columns. As I said, the most useful are the first 18 or so that we show. And what's important to note is that for Alminer, we actually show one row per spectral window that was observed. So, for example, when you go to the archive and you look at a given project, if you want to know its spectral setup, you have to hover over the frequency support, and then you can see that there are, for example, here, 4 different spectral windows. They start at 343.08 gigahertz to 344.96. And so what we do is we actually split these, and each of these become one row in our data frame. And you can see we've also converted the minimum frequency, maximum frequency in gigahertz units. So you can see exactly where a band starts and ends, and what's the central frequency, the bandwidth, and then the frequency resolution, the velocity resolution, whatever you may be interested in, that on the archive you have to hover over, but here you will get it as actual columns. Okay. So yeah, as I mentioned, all rows equals true may take long for large queries. Now, the search results can be further narrowed down, like I said, with pandas data frames. So here, for example, we can try something. We can whatever query you had, so in our case, observations, you can get the names of the columns by typing like observations.columns. I will show this to get a list of all the columns that are there, and then you can know what columns you can use to filter with. If you're ever unsure about description of what a given column is, like if it's called T minus min and you don't know what this could mean, we have created a function called getInfo, where if you put the column name inside, you will get information about the description of the column and the units of the column. And then you can filter it further and then print the summary, how we had it in the query section. So let me just run through this example. So for example, the query that we had, observations.columns, will print for you all the possible 81 columns that I was showing in the table. And then let's say I want to know what the column ang res arcsecond could mean. This one is kind of descriptive, but you can see if you do alminer.getInfo and the name of the column, that you will get the description that this is the typical spatial resolution and that the units are arcseconds. So now, what if we want to narrow down our observations to only observations with angular resolutions less than 0.5 arcseconds? To do that, we basically create a new data frame. In this case, selected is what I called it. And the way the pandas kind of nomenclature works is that you say, okay, I want all observations where the observations where this column, so angular resolution arcsecond, are less than 0.5. And since we knew the unit was in arcseconds, we can just do 0.5 here. And now that we have basically down selected all the observations less than 0.5 arcseconds, we can print the summary. So we do alminer.summary, and then we put the name of this new data frame, which is called selected. And you can choose again if you want to turn the print targets on or off. Okay. So this is just an example of what you can do. There are many, many other things you can do. In this example, I'm showing how you can combine your filtering. So what if I'm interested in angular resolutions less than 0.5 arcseconds, but also velocity resolutions that are less than 1 kilometers per second? So in this example, you can say, okay, I want all observations less than 0.5 for the angular resolution and velocity resolution less than 1 kilometers per second. And then here again, you call the new data frame whatever you want. So I called it selected, and then you can print the summary of that. So you can see that you really down selected to many less observations. Okay, now what if you're interested in knowing whether a certain frequency was covered in the data frame that you created, in the query that you created? You can do this using the columns that I mentioned, so the minimum frequency, maximum frequency. They're both in gigahertz units, so we can first create or tell it what frequency we're interested in this case, 220.5 gigahertz. And I can say, okay, I want all the observations where basically this frequency lies within the minimum and maximum of that spectral window. And again, print the summary of what this subselection was. In this case, 6 projects, 5 different targets. To make that, what I just showed, simpler so that you don't have to write too many pandas codes, we've actually kind of wrapped it around into a function that's called line coverage with some extra functionalities. So for example, if you're coming from a high redshift universe, you may not want to always calculate yourself where the frequency should end up. So in this alminer.line coverage function, we give you this functionality where you can specify a given line frequency, but also specify a given redshift, and it will give you the results directly. In this case, for us, we also have the option of giving a line name, but it's important to note that this line name is just what for the user to keep track of. It's not, it doesn't really mean anything. So here I'm showing in this example that, for example, I was interested in the line frequency of 220.5. The default is redshift 0, and I want to call it my favorite line. and I want to print the target names. So in this case, it will write you a summary of my favorite line observations at 220.5 gigahertz corresponds to this query. Now, the example for adding a redshift is the following. So you basically follow exactly the same thing as before, but you just give it a different redshift value. And what it does is it will actually print for you what frequency got shifted to. So it says that your observations at 400 gigahertz, which is what you requested, corresponds to a redshifted frequency of 266.667 gigahertz at z equals 0.5. Okay, we have included some of the most common lines, so CO, 13CO, and C18O, so all the frequencies that are covered in all the ALMA bands into a given function called CO lines. So with this function, we can determine how many of these CO and its isotope logs were observed in your given data frame. So an example of this is I call my new data frame CO ops, and I call CO lines. So I put the data frame that I had originally, and it will basically go through all the CO and its isotopologues covered in the ALMA band, which is quite a lot. So here we can scroll through. For example, we start at CO 120, and it will tell you that the observations are at, well, CO 120 is at 115.271. And these are the number of observations that covered this frequency. And then you keep going, CO 221, 322. And then if you keep scrolling, you come to 13 CO. And then at the end, C18O. Yeah. So another example where you now want to provide this CO lines redshift. So in this example, I've said, okay, my target is at z equals 1. And then it will do what I showed before, where it will shift the rest frequency of CO to the redshifted frequency, and then it will summarize for you what there is or isn't. Okay, now everything we did with the filtering can be visualized, so you can see better what you're looking for and help you kind of guide your quest. So for the plotting routines, we have a few different routines. Most of them are sort of overviews of observations, overviews of given lines, given frequencies, the sky distribution, etc. So I will go through this list now to show you all the options for plotting. So for all the plotting routines, we have, well, for most of them, we have a few options that are in common. So we can mark certain frequencies on the plots. This is done by setting mark underscore frequency parameter. And for CO in particular, you can set it to true. So it overlays where the CO lines and its isotope logs are. You can specify a redshift if your target is redshifted or is at a higher redshift. And then you can also have the option of saving the plot that was created. And if you want to really do things in loops and automate it, and you don't want to be like for the program to pop open all these images, you can always turn show figure to false and just run everything sort of passively. Okay, so the first function is plot overview. Plot overview will plot a summary of observed frequencies, angular resolutions, largest angular scales, and the frequency and velocity resolutions. So let's look at an example. So for the data frame that we had, so I just call Alminer.plot overview. I feed it the data frame, and I tell it to save the figure in a file, that whatever you want to call the file. So in this case, I called it Alma Galaxy Chemistry because that was the scientific keyword that we used. So in the plot, what you will see is the number of observations as a function of frequency. So this is the distribution of observations as a kind of function of different bands. The bands are colorized, and the y-axis is in log units, so that you can really see, for example, if higher bands are usually there are less observations of, you can kind of also visualize that properly and see. So for example, in this case, tens of observations in band 8 and 9. And we also write a summary of how many observations there were done in each of the bands numerically as a quantity, so you can know. Then here you see the number of observations as a function of beam size, then as a function of largest angular scales, frequency resolution in kilohertz, and velocity resolution in kilometers per second. Okay, for a given line that you may be interested in, we can make the plot that I just showed basically highlight a given frequency. So in this example, I'm showing the same plot I had before, but I want to highlight the line frequency at 100 gigahertz. So in this case, you have that plot I had, but in hatched, you can see all the observations that are at 100 gigahertz. And here we also split it out to tell you how many of these 370 observations cover this line frequency. And the reason why here, so this distribution that we show is based on the central frequency in the table. So that's why also it's also depending on the binning, you may get multiple bins highlighted. If I can show you here better. So this is the view that you have. You're just looking at the Jupyter notebook. Let me just scroll down to where we are. Yeah, this is easier now. Perfect. So here you can see what I was talking about. So it will also highlight in the plot, the overview plot of angular resolution, largest angular scale, frequency resolution, and velocity resolution, the observations that cover the line frequency of 100 gigahertz. And we also write out what the minimum and maximum values are, because that may be really important to you. Like sometimes they may not be very easily visible if you have like a really big dynamic range. Okay, let me keep going here for the plotting routines, and then I will switch back to the other view. So in the case where you have a redshift, basically the line frequency will get shifted. So here we were interested in 400 gigahertz at a redshift of 2. So now it's showing up around 100 and some, and there are 6 observations that covered that frequency. For the next type of plot that we have, we make an overview of all the observed frequencies in each band. So we do zooms of each band so that you can see the exact coverage in each band better. So in this example, so the function is called plot bands. You give it the data frame, and you can choose if you want to mark the CO and its isotopologues, or give it a redshift if you want. So in this particular example, you can see that this is the same overview plot that I was showing before, but that now we have these zoom plots for each of the bands. So band 3, band 4, 5, 6, 7, and 8, and then overlay are the CO lines and their isotopologues. So even in the zooms, you can see where the CO transitions lie. Okay, let's keep going. What if you're interested in a line that is not CO? You also have the option of giving a list of frequencies so that you can just visualize where they would lie in this plot. And those are drawn as these vertical dashed lines. So I just gave 3 random frequencies, and they're also shown in the zoom plots here. Now, if you're interested, so like I said, these histograms that are plotted are based on the central frequency of the spectral windows. But if you want to know exactly where a band starts and ends, you can use the next function that's called plot observations. So in this case, you will see exactly like the data frame that you had, but visually. So in the x-axis, you're seeing the observation number. This is really meaningless. It really depends on your data frame and the table that you created. So this is the number in the table. Like if I can scroll back up and maybe not, hopefully make you dizzy. In this table, it would be the observation number. So it really depends on the query that you made and the filtering that you did, etc. But what you can see, which is really useful, is the distribution of the exact frequencies. So here you can see where a given band starts and where it ends for each of the observation numbers in your data frame. And then you also have the option of marking the CO lines on the plot. So here, for example, this was very dependent on the data frame that you created, right? So some observations were called at row number 700 something, and now some are around 1000 something. But it's really useful to see these kinds of plots. Again, as before, you have the option of marking certain frequencies rather than CO, and it will draw horizontal dashed lines in these cases for the frequencies you requested. We also have the option of plotting the sky distribution. This is really just perhaps well, it's interesting. I always find it for galactic studies interesting how everything is on one plane, but you may be interested in making sure that your query is not kind of catching some outliers by mistake, and you can investigate at least further based on that. So this function is plot sky, and you just feed it the data frame. Okay, let me try to go back and go through get through all the plotting and go to the next section actually. Perfect. So this section now discusses how you can make reports of everything you just did. You have two options. One is to create a table from the data frame in as a comma separated table. And the other is to save all the plots you created. So let's go through these options. The first one is the save table option. It will save it as a CSV file, and it will save it in a folder called tables in the current working directory. And if it doesn't exist, it will create it. So you don't need to do anything in that sense. So here's an example. Went too fast. You can save a table, the observations data frame that we had, and I called it Galaxy Chemistry. You can see if you go to the GitHub page where this is hosted, that now there's a folder called tables, and this file now exists there. Okay, and we can now save plots. So it will create, if you call this save source reports, the function will create these overview plots that I showed you, but it will create it for each source. So you will basically have a report per source in a folder called reports. So this is kind of interesting if you're interested in I'm trying to say that it's difficult if you have a really, really large data frame, then you will end up with like hundreds. Let's say if you have thousands of sources, it will create thousands of plots in this folder. But if you're interested in a particular target like TW Hydra or something, then you can use this save source reports to create individual plots for each source. Again, if you go into the reports, you can see all the different, so in the example that I ran, we had, I think, however many, this is 8 or 9 different sources. If you click on each of them, you can see that it has saved this overview plot. So this one had only band 3 observations, and then you get the overview plots for each of the sources. Okay. Let's keep going. So you can also make sure that CO lines are marked on these overview plots. Let's see. Oh, I think yeah, so in this example, we are first narrowing down our query because, yeah, maybe you don't want to save like thousands of, the reports. That's exactly what I did here. So I just narrowed it down first to observations with angular resolution less than 0.5 arcseconds and only observations in band 3. So I just kind of used the minimum frequency, maximum frequency to choose that. And then it told me that there are 8 projects in these different sources. And then I created the source reports. And that was exactly what I just showed you, the folder that I showed you. Now the grand finale is the data download option. So you have the option to download data directly from the archive. This is why we have the default as only querying public data sets, because you will have issues with the proprietary data. But the general notes about the data, the download function is that you can select your desired location. So you can basically give whatever path you want to the parameter that is called location. If you don't, it will be created within the workings directory in a folder called data. You can check the amount of disk space that you have by setting the dry run to true. I really recommend this just so you make sure that nothing is crashing. Also, it's not just for the disk space, but to make sure that it's exactly what you want. And then you also have the option of downloading either the raw data or only fits data. And if you want fits only, you set the fits only parameter to true. And what's really nice is that you can specify a certain file name parameters, let's say, that you want to be in the file that you want to download. So for example, if you want to only download continuum data, you may want to include .cont in, you may want .cont to be in the file name. This is very, very dependent on the cycle of data and how the data products were created, what naming scheme was being used throughout the last decade. So I think we're going towards actually a better system with a new pipeline where typically if you're interested in your science target, the actual name of the target will be in the file name of the FITS file, or there will be like _SCI for science. You can also narrow it down to .pbcore to kind of narrow down your download that way. And the download function will then actually print out the URLs of the links that it's trying to download, which is really useful because you can just set dry run to true and just print the URLs, and then you can even click on the URLs and download whichever you want, like manually by clicking. So let's look at some examples. So here, the down selected data frame that I had created. I want to download data, but I don't want the fits only. So I want the tar file with all the raw data and the fits. I set dry run to true. I tell it my location as a path, and I tell it to not print the URLs in this case. And what it does nicely is that it prints for you the MOUSs that it is trying to download, so you can always double check things. So you must know that these your MOUSs, you can then just, if you wanted, you could go to the archive and insert it in member OUS ID here, just to make sure it is what you want. And then it will write for you how many teras or how much data is needed and how many files will be downloaded. So if you set dry run to false, then it will go ahead with the download. If you're interested in fits only, then you set the fits only parameter to true. And in this case, I've included some restrictions for what should be in the file name of these fits files. So I wanted _SCI, pbcore, and cont. And here I'm printing the URLs. So if I click on any of these, it will open for me my Finder window where I can physically download the data by clicking. Okay, so that was kind of the tour de Alminer. To wrap things up, I want to remind you that the documentation is on Read the Docs, so you can click on this link. I really recommend you to look at, so if I click on this, to look at the API. Here we have all the descriptions of all the parameters that are in each of the functions. In the landing page of the documentation, we have the tutorial, more or less what I just presented to you. And if you go to any of these tutorials, you can click on these functions. So here, if I wasn't sure what Alminer Explore does, I can click on it and it will take me to the API where I can see exactly what parameters I should give it in what format, etc. So that's really useful. And for updates, the GitHub page will be having the cutting edge version. We will do pipey releases so that you can pip install them when there are some major changes that have been made. If you do use Alminer and you find it useful, we would be really appreciative if you could cite us. We are currently in the process of getting a DOI assigned, so please check our GitHub page to see the exact ADS reference once that's assigned. And I also wanted to acknowledge the work of many Leiden University master students who were involved in the very, very early stages of the development of this code, particularly Robin and David, who worked with Alvaro mostly before I joined Allegro. I'm sure it was very fruitful and helped where we've gotten. And yeah, if you have any issues, any questions, you can open issues or ask questions on the GitHub tracker, or you could email us. You could email me and Alvaro directly, or you could even email Allegro and it will come to me. And thanks for using Alminer. Thanks for being interested, and good luck mining the Alma archive.